Um, Also, we are gonna have a quiz on Thursday. This quiz should cover the same topic of the lab: shift, rotate, Boolean operations, also bit manipulation. Okay. So last time I started to explain stack. S- So today I'm gonna complete it. So we are very close to finish this chapter. All what we have here is a stack and subroutines. How can you make subroutines and how they work? Okay. After that, we are gonna start chapter 3. By the way, before I forget, the first Thursday after the break will be the first test. It should cover chapter 1 and chapter 2. Okay, guys? So it's going to be during the lab session. Okay? So the first Thursday after the break, we don't have a lab. Instead, we are going to have a test on chapter 1 and 2. Okay, guys? This is test 1. Okay, so let's now explain. Last time I told you we have something called a stack. Okay, very important. We are going to use it all the time. Very useful. So what is a stack? The first definition for a stack, I told you, this is a section of the memory. So we take a part of the memory and use it as a stack. Okay, so as long as a stack is a part of the memory, that means a stack is used to store data for sure. That's the only thing memory can do. That's just to store data. That's true. So a stack is a storage unit. That's true. It can store data. However, we already used memory before. Okay, you remember load, store, and move instruction. All these instruction we used memory before. However, a stack is little bit different. Okay, because the way we used the memory before, we call it random access. Why it is random? Because you can access locations randomly. So I can go to location 1000 and then I go to 7000 randomly, right? However, here in stack, it is a memory, but the way we read or write different from what we did before. It is not random anymore, but there is some way to read or write, okay, which is, as I said last time, last in, first output. So the last data you write is the first data you take from stack. Okay, and I give you very good example. If you have a stack of plates, as you see here in this picture, let me maximize this one. Yeah. Okay, so if you have a stack of plates like this one, guys, okay, if you want to add one plate here, where you have to put it? You have to put it here in this location, right? I cannot put it in the middle. I have to put it here, right, on the top. Also, if you want to take a plate, which one you have to take? For sure, you shouldn't take this one. Otherwise, all of them are going to be broken. So you have to take from the top. Same idea. Stack, you can imagine now every plate here like a data, like a byte or word, right? So same thing for stack. We have a certain location. We call it, this is the top of the stack. This is the top of the stack. So every time you write on the top of the stack. Every time you read from the top of the stack. So there is a certain point to write or read, right? That is why you will notice different from what we did before. So what we did before, guys, if I want to read or write a memory location, I have to tell which memory location, right? In case of a stack, I'm not going to tell, right? I'm not going to tell read this location or that location because you don't have option. You don't select, right? All the time it has to read from the top of the stack. All the time it has to write on the top of the stack. Is that okay? I give you a very good example here, guys. As you see here, assume this is the stack and we store data here. This is the data we store. So what is the top of the stack? This is the top of the stack. So if I want to read, if I tell the stack read, right? So the stack is going to give you EF, right? The top of the stack. Okay. And now we have a new top, new top now, because this one is gone already. So this is the new top of the stack. Okay. Now if I want to read, I'm going to tell the stack read. So the stack is going to give you P1, which is the top of the stack. Now this is how the stack looks like. Okay. Then if you want to write, okay, so you have to write here on top of this one. So you can see my top of the stack was 1005. Now it's 1006, 1007, and now after I write again, it is 1006. Okay, guys. So you can see the stack it's much like a variable length array. Okay, so every time you write to the stack actually grows. Every time you read from the stack shrinks, as you can see here. Is that okay? Always, also, there is always what we call, there is a certain address we call this is the top of the stack, right? So how, where this address is stored, who's gonna, someone has to keep track of this address. Okay, yes, that's true. Which is the stack pointer. Okay, so we have a stack pointer register. This register is 16 bits. This register should keep track of the, so here this one is stored to this one here. Once I read, stack pointer should be this value. Once you read, stack pointer should be always keep track of the top of the stack pointer, right? It's very similar to a PC program counter, right? So also program counter has to keep track which instruction I have to execute right now, right? Every time you execute one instruction, PC is updated. Exactly same thing, but this time a stack pointer is storing the address of the top of the stack. Okay, very simple. So if you want to add something to the stack, I have to add it on top of the location stored in stack pointer, right? If I want to read something from stack, so I have to read the data stored at the location pointed by stack pointer, and also I have to update the stack pointer. Every time you read or write, a stack pointer has to be updated. So here stack pointer is 1005 because this is the top. Once I read something, it's going to be 1006, 1007, and then 100736 again. Okay. So let me go to the, so this is much, this is exactly what I explained. It's a part of the memory. I'm going to reserve it for a special purpose. We call it a stack, right? Until now, it's not clear for, no, until now, I'm just making a definition. I'm defining what is a stack, how it works, but I didn't explain for sure yet how it is useful, why we need it, okay? In what case? Because it looks some kind of weird. Why the last data in is the first output, right? There should be a reason. Is that useful in some cases? That's true. That's what I'm going to explain right now. How this is useful in some cases, I'm going to tell you how, right? Last in is first output. For sure, they made it this way because it is useful in some cases. That's true. Okay, so I'm going to give you details. Don't worry about that. Okay, so now I'm going to update our memory, okay, map, so that now I'm going to add the stack to it. Okay, so when you write our program, what we did in this semester, we start from 4,000 and then we go this way to write our code, our program. I told you this flash memory. That's what we did so far in the whole semester. Also, for our data, we start from 1,000. Okay. Now, my stack is going to start from here. So my stack is going to grow this way. So I'm going to start from here, from 4,000. Okay. But 4,000 is going to be code, not it's gonna it does not belong to stack. So stack is gonna be just above 1,000. It's gonna grow this way. Okay, guys, grow this. So you can see here, guys, our stack here grows from big address to lower address. That's true because every time we decrement the address, so we grow this way. Okay, I want to tell you something important. If you learn one microcontroller, it's easy to learn others because you're almost the same. Okay, but sometimes there are very minor differences. So one of the difference you may find in other processors is that the stack grows from small address to big address. That's it. So it's the same idea, everything almost the same, but stack here in this processor and other processors also, the stack grows from big address to smaller address, grows this way. In other processor, it may be the other way. It's not a big difference anyway. Very important point. Listen to me. Very important point. Okay, guys. I told you before, we don't have operating system. So who's gonna make a management to the memory here? Is there anybody should make management? No, you have to make the management by yourself in your code. What this means? It means if this is memory, right? If you keep writing data, you may write in the stack area. You got what I'm saying? So clear, they can make collide. Okay, for sure you're gonna destroy the stack. So don't expect after I damage my stack, the data stored in its stack, my program is gonna work correctly. Don't expect that. Okay, same thing. If you write data, maybe you go to the data area and damage it. Okay, guys. So that means you have to make sure, okay, the maximum size of your stack, okay, is not gonna come to the data area here. So you should not, you should have a limit. You should have a limit on how much data you can store, because if you store too much, you're gonna go to stack. Same thing, you should have a limit on how much data you store in the stack, because if you store too much, you're gonna go to the data here. This is your responsibility. Again, this is hardware. We don't have operating system. That means if you tell the stack write, the stack is not going to tell you stop. The stack is not going to do that. It's not going to tell you this is the area for your data. You're damaging your data. It's not going to tell you that. Okay, guys? So you have to do it by yourself. Yeah. So anyway, I think for most of our programs, it should be okay. From 1,000 to 4,000, there should be enough space. But you have to keep this problem in your mind anyway. Okay. I'm going to explain this one in the end. Okay, so now I want to tell you something, guys. I'm not going to say again, because this is not the professional term, right? Yes, we write, but usually we don't use in stack, we don't use the word write. We use the word you push. You got what I'm saying? So if you push, that means you write to the stack, right? For reading, if you want to read, we use the word pull. So when I talk about the normal memory, usually I use the word read and write. But for stack, usually I use the word pull and push. Okay, push means write. So I'm explaining here how it works, how the hardware will handle it. I'm going to tell you. We have an instruction. I'm going to explain it right now. This instruction is called push, right? Push register A. It means I want to store the value of register A in the stack. So how this instruction is executed, okay? It should be executed this way. A stack pointer, for example, should point at the top of the stack. Now I want to write. So I want to write a byte. So number one, a stack pointer has to be -1. So I have to decrement 1 so that I can go to empty location, because this is the top of the stack, right? So it has to be decremented by 1 so that stack pointer can point at empty location. And then at the location pointed by the stack pointer, we're gonna write the byte. Okay, guys, this is how it works. Again, I'm very clear. I'm not saying in order to push you have to write 2 instructions. I'm not saying that. What I'm saying, we have instruction, we call it push, right? I'm explaining how the hardware will do it. Okay, how it works. Okay, all what you have to say, just push A, push B, right? So once you say push register A, as you will see right now, when the instruction is executed, 2 things are gonna happen. Number one, stack pointer should be subtract 1 to go to empty place, and then you have to write the byte in this place. Okay, so that you can add now on top. Is that clear, guys? As you see here, and now I have a new top for the stack. For example, if the stack pointer was 1005, after I push 1 byte, now it is 1004. Makes sense, right? Any question? Any question in this slide, guys? Is that clear? Okay. Now, what if you want to pull? What if you want to read? How it works, right? Look here, guys. Here we subtract first, okay? Because I want to go to empty place. However, if we pull, for example, this is the top of the stack. The top of the stack is at 1005. I want to pull 1 byte. How I can do that? Very easy. So I'm going to go to the location pointed by stack pointer. okay, which is 1005. I'm gonna read whatever is there, which is 3A, right? I'm gonna read it. Number two, I'm gonna add one, okay, because already this is not the top anymore, because I already took, it's like a plate. I already took this plate, right? So stack pointer, you have to add one to come here, right? As you see here. And now this is the top of the stack. So this is outside. You can imagine this doesn't exist, because once you write, you are gonna overwrite on it. So now I have, this is my top. Okay, guys, any question? You can see what happens here. Very easy. So we use the stack pointer as a pointer. If you want to pull, you are going to read a byte at the location pointed by the stack pointer, and then update the stack pointer by adding one, right? Again, I want to repeat something here. Don't be confused. I'm not saying you have to write two instructions as written here. I'm not saying that. I'm saying how it's only one instruction, which is pull. I'm explaining how pull is going to work. Okay, guys? Any questions? Now, you can guess, what if I want to push a word instead of byte? How it works? It's exactly the same thing. The only difference here, I'm going to subtract 2. So here, instead of going 1 byte up, I'm going to go to 2 byte. And then I'm going to write a word, right? That's it. So the only difference here, I'm going to subtract 2, because I have to have two empty location here, not only one. Same thing here. Okay, if I wanna read the word, so I'm gonna read two bytes, okay, starting from the location pointed by SP, okay, and then I have to add 2, because now I have to remove 2 bytes, so that I have new top here. Is that clear, guys? Please. So if anybody doesn't, before I move forward, before I give you details, if anybody does not understand, okay, number one, what is a stack and how it works, right? Please let me know. Unmute your mic and talk to me, okay? For sure, don't ask me how we will use it, because I didn't explain it yet, right? So I'm gonna just give me 1 minute. I'm gonna explain right away. I'm gonna explain how very soon how we use it, but at least you should understand it. You should understand the idea of last in first output. Okay, you should understand what is the rule of the stack pointer. You should understand push, how we pull, and so on. Any question, guys? Okay, so let's see what instruction we have here for push and pull. Okay, don't forget, push means you write to the stack. Pull means read from the stack. Also, don't forget, when I read or write from stack, I'm not gonna give address. This is completely different from what we did before. What we did before, load instruction. Can I say load? That's it, or you have to put address? I have to put address, right? Here, I'm not gonna do that, because you cannot read or write from anywhere. It's not random, right? So it has to always be done at the top of the stack. Okay, guys? So let's first see push instruction. We have three push instruction for bytes. So every one of these instruction push a byte. So we have push A, we have push B, register A, register B. Okay, we have push C, which is the CCR, which is a flag register. Okay, for word we have push G, push X, push Y. So this all what we have, right? Can you push a memory location? No, we don't have one instruction to do that. But again, as I said multiple times before, that does not mean you cannot do it. You can do it. All what you have to do, you can take the value, put it in one register, and then you can push register as usually we do. Okay, guys? For pull, we have exactly same instruction here for pull, exactly same instruction. So for bytes, pull A, pull B, pull C, pull D, pull X, pull Y. Okay, guys, any question? Is that clear? Okay. Okay, guys. Okay, so let's move forward now. I want to give you just a couple of examples to understand this instruction better before I come to the important point, why we need how we will use it. Okay, so let's start with the first one here. For example, if I say push A, what push A should do? Push A should copy okay, copy register the content of register A and to store it on the top of the stack. Okay, for example, eh, eh, this is register A is storing the value 3A. If I say push A, so after I say after execute the instruction push A, so the stack should look like something like that, 3A, and the stack pointer is pointing here at the top. Okay, so the top, before I do that, the top of the stack was here. I added 1 byte and the stack pointer moved to here. Okay, so let's see also if I do something like bol A, bol A. So look here, assuming this is the stack before I bol before I execute this instruction, this is the stack how it looks like, right? So SP is pointing at the location 1005. Again, I give you some just examples, okay? Don't because I told you are gonna start from 4,000. For sure, I'm not gonna go all the way to 1,000, but I just use any number here to explain the idea. Okay, so here stack pointer is pointing at 1005, just any number, and this is the top of the stack, ff, right? This is a byte stored at the top. And bol A, because we are gonna bol a byte, so bol A. Okay, so what's gonna happen, I'm gonna get the top of the stack, which is ff. I'm gonna store it in A, right? So this is where, so you are gonna read uh, a byte from the top of the stack and put it in A. That's why after you execute this instruction, A should store ff. And now this is my stack is like this one. It was here, look here, 1005. No, now it's 1006. Okay, remember, every time you push, the stack pointer should be decremented, and every time you pull, you increment. That's why here it was 1005, now it's 1006, because we pulled, I pulled 1 byte. If you pull a word, it would be 1007, right? If you pull one word. Any question, guys? Okay, let's explain why. Okay, how we can use stack. Okay, I'm gonna tell you why. Okay, number one, I already explained this one before, even I explained it in the lab. So let me tell you what is the problem and how can stack help us here. Okay, so let me first explain the problem. The problem is I want to make for loop 10 times, right? So look at this one here, load A at 10. Look at the word loop here. Look at the decrement here. Okay, guys, don't look at the rest. Just look at this one, and this one. This is how I created loop 10 times. Okay, so I'm gonna start from number 10. Every iteration, I'm gonna decrement A, and if it is not 0, go to loop. Come, decrement A. If it's not 0, go back, and so on. Okay, guys. So here I used register A as a counter, and I told you before, A should have the value 10, 9, 8, and so on. So every iteration I have to decrement to 1. Once it's 0, we're going to go outside. However, I told you here in the body of 4 here, maybe I want to use register A for something. I want to multiply, division, whatever. So I want to use register A, right? So if you use register A and it changes this counter, the counter, if you change this value, you are not gonna make correct for loop. You got what I'm saying? Because to make correct for loop, A should be counter, right? So it has to be 10, 9, 8, 7, and so on until 1, and then 0, and so on. You got what I'm saying? It has to go this way. Okay. So what can we do now? So A is reserved as a for counting, or as a counter, right? In the same time, I want to use A. So what can I do? I told you a easy way you can do it, guys. In the lab, you can do something like that, guys. As I told you, for example, I can store the value of A, which is a counter. I can store the count. I can store it, for example, in any memory location, for example, 1000, and then I use A. But before I come here, I'm gonna pull, sorry, this 1000 and this 1000. I'm gonna get it back, put it in the register A back, so that now if the counter is 7, I'm gonna store number 7. Then I'm gonna use A, and then before I come here, I'm gonna get the 7 back, so that when I come here, A is storing the correct count. Okay, so this is what I told you about. However, This one has a lot of problems, okay. It's okay, it can work for only one value. However, it has a lot of problems. Number one, okay, you have to remember, you have to reserve certain addresses, okay. So if your program is long, you may forget, right? You may forget, or it's going to be difficult in programming to remember. Okay, register A, do you remember where I put it? So I have to get it from the same memory location. Another problem, what if you have too many, you have to push a lot of data, get a lot of bit data back. So anyway, this is not very convenient. It can make errors. It's gonna work, I'm not saying no, it's gonna work, like but it is not professional to do this way, okay. The other way, because I have to remember what addresses, I have to reserve these addresses to remember what addresses, okay. So the other way, I can simply stack does not need addresses, right? So all what I can say, push A. So I'm gonna store the value of A in the stack, and then I use A, and then when I come, I'm gonna tell pull A, give me A back. You got what I'm saying? So it's gonna do the same thing like this too, but for sure, this is very professional, much better. I don't need to remember what addresses to get and so on. So all the time we're gonna do that. Push A, right? And then use A, and then when you need it back, you can pull A back. So this one is gonna store the value of A, which is a counter, right? The count, and then pull A is gonna get the count from the top of the stack, is gonna store it in A, so that I decrement it here and keep looping this way. Okay, any question, guys? So I can use it for temporary storage of data this way, right? Any question? Is that clear? Okay. There are other things I can use the stack for, guys. For example, and I need you to think about it a little bit. If I push A and then push B, okay? So now the top of the stack is B, right? But if I pull, I'm gonna pull in the same order. Here I push AB, I'm gonna pull AB, okay? Look here, think about it. I'm gonna push A, push B. Then when I pull, I'm gonna pull in the same order, AB, AB, right? So actually, if I do that, I swap A and B. You know why? Because I'm gonna add A, the value of A, and then I'm gonna add the content of B on the top of the stack, right? So now the top of the stack has B, because it's last in first output. So when I get from the stack, I'm gonna get B first and then A, right? Because last in first output. So here, when I tell the stack, give me a number, the stack is gonna give you the last one, which is B. So B is gonna go to A, and A, which now after I pull, now the top of the stack should have A, right? So it's gonna come to B. So the conclusion is, listen to me. If I push A, push B, and then the same order, pull A, pull B, actually what you did is swap. Okay. However, if you reverse the order, if you pull in opposite order, actually is gonna be you do nothing. It's gonna be no change. Okay. For example, if I say push A, push B, and then I'm gonna say push B, push A, right? So I did nothing, right? Because here you push, the last one was B, and then the first one I'm gonna get, it is B. Okay. And this is very useful. You know, we're gonna use it all the time. I'm gonna tell you why it is very useful. Look here, guys. If I do something like that, I'm gonna say, especially let's first do I'm gonna explain this one. I'm gonna tell you how it is useful and how we're gonna use it all the time. Okay, look here, guys. I'm gonna push A, push B, push X, push Y. Is that okay? So here I store the value of A, then on top of it, the value of B, the value of X is gonna take 2 locations, the value of Y is gonna take 2 locations. So now the stack is storing Y, then X, then B, then A, right? And then here, I'm gonna damage, or I'm gonna use A, use B, use X, I use Y, okay? When you wanna return the original values back, so here I wanna store the original values, and then I'm gonna change all the register. Now I wanna get the original values back. All what you have to do, you have to pull, but it has to be in the opposite order, right? The last one has to be first one. So here I have to say pull Y, pull X, pull B, pull A. If you do that, the same value you push here is going to be the same values you get here. You got what I'm saying? Someone can ask me, okay, so what did you do here? Okay, here for some reason, okay, register A, B, X, Y are storing some values are important. I need them, right? However, I want to change this value, okay, and then after some time I want to get the original value back, right? So here, this bunch of push instruction are gonna store in the initial values. Then I can change A. Use here means change. Use it in multiplication, in division, and so on. When you need the value, these values back, you can just pull them. However, you have to be careful. Why you have to be careful? It has to be the opposite order. So if I push A, B, X, Y, I have to pull Y, X, B, A, right? So that every register should get its original value because it's lost in first output. So after I push A, B, X, Y, when I get from the stack, I'm gonna get Y first, and then I'm gonna get X, then I'm gonna get B, then I'm gonna get A. So that's why it has to be reverse order. How this can be useful? I'm gonna tell you how. We're gonna use this one all the time. I'm gonna tell you how. Okay, just 1 minute. Yes, right here. Yeah, it is useful here, guys. Look here, guys. As I'm gonna explain shortly, I'm gonna explain subroutines. You know what subroutine is, right? Function or subroutine. Okay, if you have a function, you call you know how it works, right? So in the main program, you have a function. I'm gonna elaborate later anyway, but just let me explain it quickly, and later I'm going to give you the details. Okay, so this is the main program. Once I come to the function, I'm going to call the subroutine. I'm going to go to the subroutine, and then I'm going to come back, right? Come back after the subroutine. Okay, call is not an instruction. I'm going to explain later what instruction you have to use. I'm just explaining the idea. So once I come here, I'm going to go to the subroutine, and then I'm going to get back. So what is the problem and how stack is going to help us? I'm going to tell you. Look here, guys. This is my main program, right? Here, I store some value in register A, I store some value in register B, some value in X, some value in Y, right? For example, A is storing the number of cars, right? B is storing, for example, the temperature or speed, whatever, okay? X is pointing at one array, Y is pointing at another array, okay, guys? So, and still I need to use these values later. After you call, still I need to use X. I am gonna use the value of X, value of Y, the value of A, the value of B, right? So it is a very good programming habit. It is very good programming habit that the subroutine should not mess up with your main program. What you mean by mess up? I mean, if you call the subroutine, and subroutine is going to change all the registers, right? So the problem I'm going to have here, the values I have here is going to be different from the values here. You got what I'm saying, guys? So your program is not going to work because here, after the subroutine, you are thinking X is pointing at a certain location in memory, but no, you already damaged it, because when you went to the subroutine, inside the subroutine you used A, B, X, Y, and you damage it, right? So how can we solve this problem? It is important. It is a good programming habit that at the beginning of the subroutine, any register you want to use, just push them and then use them, and at the end you have to pull them back. Why? So that before you call a subroutine or after, all the registers should have their initial value. This one, so if you already put here speed, so after you call the subroutine, still register B is storing the speed. You can just use it, right? You got what I'm saying? So is that clear, guys? So that is why all the time, let me go back. All the time in subroutines, we're going to do something like that, guys. In subroutines, we're going to push the registers I'm going to use, and then I'm going to pull them back, right? So that I don't mess up with the main program, right? Is that clear? The idea is clear, right? So if you store something in the main program in register A, after when you call a subroutine, the subroutine is not gonna change it. Okay, so still you can use the same value next, right? Is that clear, guys? Any questions? Okay. Another thing which maybe also you can do this with the stack is, for example, if you have the word hello, right? If you push the word hello, if you have if I push letter by letter, so I'm gonna push Hello, right? If you pull, you are gonna get it in reverse order. So because first in, last out, right? So if I push byte by byte, so it's gonna be Hello. When you pull, you are gonna get O. So you push this way. When you pull this way, yeah. For some reason, again, this is not a big issue. But what I'm saying, for some reason, if you wanna reverse, if you have something you wanna reverse, stack can do very good job on that. Just push and then pull, you are going to get it in reverse order. Is that okay? Number 3, and this is the most important thing. This is the most important thing. Stack was created mainly to implement subroutines. Without stacks, we cannot, the hardware cannot run subroutines. This is the most important thing. So let me go back, guys, here. What I'm explaining here, guys, how a stack is useful, how we will use a stack. So number 1, I give you this example: temporary storage of data. You can push some value, use a register, get it back, and then also you can swap. Yeah, but again, these are not the main ones. Anyway, same thing here. You can use it with subroutine. As I explained, you can reverse, but again, this is not also the main one, but still okay, you can use the stack for this one. But this is the most important one, as I'm gonna elaborate later. So later when I explain a subroutine, guys, I'm gonna explain why if we don't have a stack, we don't have subroutines, right? You will see, right? You will see. Again, this is done by the hardware. Your computer, your smartphone have stacks. They must to have stacks, right? They have, because without stacks you cannot run any subroutine. You got what I'm saying? Any subroutine in any language, you cannot do that on the hardware, as I'm gonna explain later. Okay, so leave this one for now. Later I'm gonna elaborate why stacks. Without stacks, we cannot implement subroutines, or we cannot run subroutines on the hardware. Okay, guys. Any questions? Okay, I think let's have see this example, but let me go to, maybe it's let's go to the slide. Yeah, let's see if I miss something here. Mm. Okay, again, I think nothing is here. If this is the initial stack, if you pull A, so the top of the stack EF is gonna go to A, right? And the stack pointer, now stack pointer is gonna be here. So this is my top of the stack, right? Uh, this value is still there, but but I'm not gonna use it, right? So when you push, you are gonna overwrite it. So I can say it's already gone, right? Because I'm not gonna use it. But you copy. When you copy, the value is still there, right? But I'm not gonna use it. Okay. So nothing here. Also, if this is the stack and you push 1 byte, so it's gonna be this way. So stack pointer has to come here. I think that's easy. Uh, Here I'm explaining exactly the same thing, but here, how can you push or pull a word? It's exactly the same thing, right? But here, you are, number 1, instead of reading or writing a byte, you are gonna 1 byte, you are gonna read or write 2 bytes. This number 1. Number 2, stack pointer should be updated by 2, right? Decremented by 2, or incremented by 2. So let's see this example. This is the initial stack. Okay, guys. Now I want to execute bull X. So what bull X means? It means I want to read the word from the top of the stack, which is EFB1, right? So I'm going to read the word, and then I want to store it in register X. So after you execute this instruction, register X should have these two bytes. Then I'm going to ask you which one is the least significant and which one is the most significant. Always in this course, right? When you read or write a word, always the one that has a small address, right, is or the first one is the most significant, right? So here I'm gonna take these two, but it's gonna be EFB1, right? So after you execute this instruction, this what should be X. Okay, again, guys, this instruction is not gonna only exchange X. is gonna also check stack pointer, right? Automatically, right? So after you execute this instruction, after you read these 2 bytes, now the stack pointer is here. So you have to add 2, right? It has to come to here. So after you execute this instruction, this is how the stack, forget this 2 because it's already out of the stack, okay? So now now the stack, my stack is shrinking because it was 4 bytes, now it is only 2 bytes, right? Shrinking. Also, the top of the stack was 1005, now it is 1007, right? Now I want to explain same thing, but for if you want to push instead of pull. So if this is your initial stack and now I want to push X, and the value of X was is storing this value, right, in X. That means this value I want to put it on the top of the stack. As you see here, the top of the stack was 1005. Now because you are pushing a word, I'm gonna have 2 location more here, right? So here and the stack pointer should be, it was 1005, it's gonna be here 1003. Is that okay? And now it is 3F5C, as you see here. Okay, guys. This is an instruction I already explained. Okay, let me see if I have more. Yeah, so here this is also another example. Yeah, for here, guys, if you see here, before you use stack, guys, you have to initialize the stack pointer. Is that okay? Makes sense, right? In the very beginning, I have to initialize the stack pointer. For example, here I can use load stack pointer, and then you can put a certain number here. Okay, I told you you can put any number, you can put your stack anywhere, but I told you guys what I want you to do, we start from 4,000 so that we can use the whole space we have for data and for stack. But technically, you can do whatever you want to do, right? I'm not saying in all the time you have to start your data from 1,000, your stack from 4,000, and also your code starting from 4,000. I didn't say it has to be this way, right? I'm saying this is the best way so that you can use the whole space, right? But technically you can put it anywhere. So for example, here, if I say load stack pointer 1006, so my stack pointer is going to start from 1006 if I want to make it this way, okay? And now I'm going to put 20 in register A, okay, guys? And then I'm going to say push A. So here, look here, stack pointer, it was 1005. When it is 1005, it doesn't mean, okay, in the very beginning, before I push, listen to me because I know a lot of students are confused here. Look, guys. Now, number one, guys, I'm saying you have to initialize the stack pointer. Okay, makes sense. You have to tell me what is the beginning. In the very beginning, you have to tell me what is the beginning of the stack pointer. In our case, you are gonna write 4,000, right? This number one. Number two. Now the stack is empty. I didn't push anything yet. Can I use pull? It doesn't make sense, right? It doesn't make sense to use pull before you use push because the stack is empty, right? However, it's gonna work. It's gonna work because it's a machine. It doesn't understand, right? So if you pull, it's gonna give you some value, but logically, it's your program is not gonna work, right? But it's gonna give you some value, right? But logically, I should not push before I pull because the stack is empty, right? So anyway, now I'm gonna put number 20 in register A. So stack pointer in the very beginning, it was here, the very beginning at number 1006, guys, right? And now I'm gonna push A. When you push A, stack pointer is decremented by 1, right? And then I'm gonna write 20. What it means? It means when you start from 1006, actually this is not the beginning of your stack. Your stack should be 1 less, right? Because this is how push is working. For push, number one, it has to decrement and then store the value, right? So if you start from 4,000, right? So it's gonna, the beginning of your stack should be 1 before 4,000, right? That is why I told you 4,000, you are gonna store code, right? Because your stack should be 1 less because we decrement first. So if I say here, my stack should start from 1006, okay, stack pointer, So actually, when I push, I'm gonna write at 1005, right? And then here, I'm gonna store number 28 in B and then push B. So now, after the first push, my stack was here. Stack pointer is here after the first push. Now I'm gonna push again, but I'm gonna push B, which is 28. So stack pointer is gonna be come here. So this is my stack so far, right? I pushed 2 bytes, that's why I have 2 bytes, and this is the top of the stack is here. Okay, guys. Now I'm gonna store this value in register X, and then I'm gonna push X, right? So after this push, before this push, the stack was here. Stack pointer was here, right? After this push, so my stack pointer is gonna be here, right? And then I'm gonna write 2 values as you see here, right? Again, the most significant should be written as a smaller address, the least significant as a bigger address. Okay, guys, any questions? Okay. Um, Here, what I'm saying here, and this is maybe something also important you should learn. Look here, guys. Now the stack, I started from 4,000 as I told you guys. Now the stack is empty. Empty. I didn't push anything. So it should be nothing is there, right? And now here, I'm going to say push A. So now I'm going to store 23 in one list, which is one list. The 4,000 should be 3FFF because it's hexadecimal, guys. Okay. It's not 3999, okay, because this is not decimal, so it has to be 3FFF. Anyway, so at this value, look, stack pointer was here, so it's going to be updated this way. And then I'm going to store 23 here, okay? Now I want to push X, right? So when I push X, so I'm going to push this value, 4567 this way, and then the stack pointer should be decremented by 2. So now the stack pointer is here, right? So here I pushed 1 byte, and then I pushed 2 bytes. So now the stack should have 3 bytes total, right? After that, I'm gonna pull X. When I pull X, I'm gonna take these 2 values, right? I put them here, this pull X, I'm gonna put them in X, okay? And now the stack has only 1 byte. When I pull A, so I'm gonna take this value, and now the stack is empty. Don't, because actually when I pull, I just copy, right? That's why I'm saying they are there. But don't be confused, please. They are there because we copy. However, you can consider they are not there because we are not going to read them anymore. Because all what you can do now, you push. Once you push, you override these values. There is no way to read, and there is no reason to read them anyway, right? Because I already stored some value until I get the value back, right? So there is no reason to read them. So anyway, you can see, guys, what I did here. I used 2 push instruction and 2 pull instruction. After this 2 push instruction, I pushed 3 bytes, and then after these 2 pull instruction, I read 3 bytes. So now the stack initially was empty. Now I pushed the 3 bytes. Now I got the 3 byte back. So now the stack is empty again. Okay, guys. Any questions? Okay. Okay. Yeah, that's what I told you. You should not, if you push, I told you we don't have programming, we don't have operating system. So you have to make sure you don't push too much, or your data should not be too much. Otherwise, you are gonna make you are gonna make a mess in your code. If you write too much data, you're gonna go to the stack area. You are gonna write some value in the stack area, and no one is going to tell you this is wrong, right? Because it's your responsibility. It's not the responsibility of the hardware. The hardware does not understand. The hardware is doing what you ask them to do, right? So if you ask the hardware to write in the stack area, it's going to write, right? If you write data, it's going to write in the stack area, right? Same thing. If you push too much, push, you may go to and make damage in the in the data area, right? So you have to make sure um, you don't push too much, or you don't write too much in the data area. Okay. Let me see here. Yeah, I think this example I already explained. Yeah. So now I'm gonna come to another important question that this you will have this question in the assignment, right? You will see this question. I'm trying to help you. I told you, look here, guys. I told you now. I'm gonna start my data starting from 1,000 and go this way. This is my data, right? And then I'm gonna start my stack from 4,000. I'm gonna come this way. And you have, as I said, you have to be careful. They should not collide, right? That means I should not push too much so that I go and destroy my data here. Or you should not write too much data to come to the stack, and you have to make sure they are far from each other, right? So the question is, how much do you need for, is it how much do you need for data? That's easy, right? You can see how many arrays you have, you can see how many variables you have, and we make all this definition in one section for all data. So you can easily it's very easy to know how much data you need for data, right? Now in case of a stack, it's little bit tricky. How much data you need for stack? It's little bit tricky. Why? It is little bit tricky because the stack is uh, in the stack, a stack should have a variable length. So every time you push, the stack gets bigger. Every time you pull, the stack gets smaller. So if you look at the stack over the time, it's gonna look something like that: 2 bytes, 3 bytes, 2 bytes, 1 byte, 5 bytes, 6 bytes. So all the time is the size of the stack, it changes. Okay. So if I ask you how big or how many bytes, or how big is your stack, or how many bytes do you need for your stack, what should be your answer? All what you have to uh, how can you figure it out? Very simple. You can see, guys, how many times you pushed before you pull. Okay, so here, or at a certain, I have to guarantee, because look, it changes. Now it is 3. So you have to make sure, in this case, if this is the case, if this is my use of the stack, I push 2 and then I push another 1 and then I pull 1, I pull 1. If this is the case, that means my stack at least should have 3 bytes, right? Because at a certain time, at a certain point of time, the stack was storing 3. In other words, how many pushes you did before you pull, right? So it has to be this one. I hopefully it's clear, right? So let me say it in a different way, and if you have any question, you can unmute and talk to me. What I'm saying, guys, in case of a stack, I need to know how much space I need for a stack, right? How can you know that? Look at your program, see uh, at a certain time, what is the maximum data you stored in the stack, right? How many pushes you did before you pull, right? In other words, right? Very easy, right? Because you have to make sure, for example, if a certain time I put 100 elements, so I have to make sure you should not write here, you should leave here at least 100 bytes here. Is that okay? Again, the tricky part here, because the stack size is very varying, varying. Every time you push, you are gonna get more space, so you have to see. And so you have a question like this one, the assignment. All what you have to see, guys, I'm gonna in this question, I'm giving you push pull, push pull, push pull, push pull. So you will see the size is variable, right? It's changing, right? So all what you have to see what is the maximum data it was in the stack at a certain point, and this should be reserved for your stack. Is that clear, guys? Any questions? Okay. Now I'm gonna move to the last topic here in this chapter, is about subroutines. Okay. And for sure I didn't finish the stack yet because it's coming right now. I told you the main reason, one of the main reasons they made stacks for subroutines, right? Without stacks, we cannot we cannot run subroutines. You will see right now. Okay, so this is coming. Now, I want to talk about subroutines, or sometimes, subroutines, they are very useful. They are used in all programming language. Sometimes you use different names to refer to the same thing. So here, in a subroutine, sometimes we say function, sometimes you say the word routine, or sometimes we use the word method. I think in MATLAB we use the word method, I guess. or Java, I guess. I don't remember exactly. But anyway, so these are different words to refer to the same thing. In this course, most of the time, I don't use the word method too much. So anyway, if I use any one of these words, they are the same. Okay, guys. So sometimes I say function, sometimes I look at the subroutine or routine. So they are the same, no difference. Okay, just different names to refer to the same thing. So let's explain. Okay, number one, let's for sure I'm gonna make a very quick revision. You should know from the C language what is subroutine. You should know why they are important, useful. You should know, right? But I'm gonna make a very quick revision so that just refreshment. Okay, I'm gonna refresh your information. So sometimes you want to use a certain code multiple times in your program. Okay, for example, I have a certain code to read a number from the keypad. In our Dragon board, we have a keypad, right? So I have a certain code. I have some code to read one digit from the keypad, right? So what if in your program, in the beginning of your program, you wanna read one digit, then after some instruction you wanna read, right? So you wanna use this code multiple times in your program. The naive idea or the bad idea without subroutines is every time every time I want to use this code, just I'm gonna repeat, right? So write the code every time you need it, right? So here I need to read the number from the keypad, so I'm gonna write the code here, okay? And then here I want to get another number, so I have to write it here. Here I have to write it here. For sure, this is not a good idea at all, right? I'm gonna tell you why. Much better idea, much better idea. Again, this is not only in assembly, this is any programming language. Much better idea, write it only one time. So instead of writing the code multiple times, I'm gonna write it only one time. And every time I wanna read, for example, a digit or a number from the keypad, I'm gonna call the subroutine. That's why you use the word you call, and then you return from the subroutine, right? So the code is gonna written only one time. Every time you want to execute it, you call and return, and so on. Okay, guys. So is that clear? Any questions? Just let me summarize in one sentence. In programming, sometimes I have a certain code and I want to use it multiple times in my program. I give you one example. If this code is for reading a number from the keypad, for example, okay? So what can we do? The naive idea or the bad idea is you can just keep repeating, right? So every time you need the code, you just put it here, right? The other idea, this is without subroutines. The other idea is to use a subroutine. This code, the code you want to use multiple times, put it in a subroutine, and every time I need it, I'm gonna write instruction to go execute and return back, call and come back, right? So here is the main difference, very clear. The main difference here, you write only the code one time. Here you write it multiple times, right? So why you are saying this idea is better? Why it's better to have a subroutines? For sure, there is a very one reason you can tell right now. If you keep writing the code multiple times, the readability of your program is going to be too difficult, because your program is going to be like too many lines of codes, right? It's going to be too difficult to read, right? Because you put too many lines. Here you just put it only one time and just you call it, so it's easier, right? So this is another, yeah. So here, if use these are the benefits of using subroutines. Number one, it can decrease for sure the program size, okay? And for sure, when you use smaller size programs, that means it's gonna take less memory space, right? As you know from this course, in every instruction you write in your program needs a memory space, right? Because it is converted to machine code, right? So number one here, this one needs less memory space than this one, because here I have to write this code multiple times in the memory. Here is going to be written only one time, right? Number two, as I told you, better readability, because here it's very confusing to read, because it's going to have too many lines. But here you are going to say call keypad, as you see here, call keypad. So when I read the program, this for human, right? For me, for human. When I read the program, it's going to be easier. Call keypad. Yeah, I know. So you are going to go to keypad in order to get a number, and then I can read. Yeah, now you got a number. So now what you are going to do is the number, right? So it's going to be easy to read the code, right? Most important thing, reusability of code. This is the most important thing, okay? What this means? It means I can write a code, I can test it, I can make sure it is working, and then I want to reuse it in different programs. How I can do that? Easy. I can make a function or subroutine, okay? And then I can use this subroutine in every program. And that's exactly what we are going to do in chapter 3. In chapter 3, I'm going to teach several subroutines you can just use. One subroutine like keypad, I'm going to tell you, you can just call this subroutine. And when you call this subroutine, this one is going to read the value from the keypad and give you this value. Is that okay? Another one, for example, you can, like, if you want to write something to the LCD, right? So we have a subroutine to do that, okay? So anyway, reusability, and even we do the same thing in Python, right? And everywhere. So in Python or even in C language, so we have already some function. Some functions come with C language or Python. You can just use them, okay? Is that okay, guys? Anyway, I don't know. I shouldn't. This is very basics. I should not spend too much time here. So anyway, subroutines are very useful. So I'm going to explain now how can we use subroutines in assembly. Any questions so far? Okay, great. Now, guys, look here, guys. In order to make a subroutine, what do we need? What do you need? Number one, I need an instruction to call a subroutine. So, for example, I can say call a subroutine. This is the name of the subroutine for sure. Okay, so I need an instruction to call. Right? And in our case here, we have two instructions. One is we don't have call instruction, guys. I'm just using the call word call. Is this not an instruction? I'm just telling you we need a mechanism or we need a way to call a function. So if you have a function, this is a function. This is the name of the function. Add any name. It can be any name. It can be your name. Any name, right? So I just use the word add. It can be anything. This is not a keyword. This is not an instruction. Just a name. So here I'm gonna call it add. So I need, number one, a way to call a function. Call a function means once I come to this instruction, I'm gonna go execute the function. And then once I execute the function, I need a way to return it back. So number two, I need a way to return. Once I hit this instruction is gonna return me back to here. You got what I'm saying, guys? This is how instruction works. So once I come here, I'm gonna go execute the instructions here in the subroutine. Once I hit a return, so I have to come to here. So number one, guys, in order to make a subroutine, I need a way to call, to go to the function. Number two, I need a way to return from the subroutine, right? Number three, for some subroutines, I need to pass some data, right? I need to pass argument or data, right? For example, here I'm assuming a very simple subroutine just to explain the idea. So here I assume this subroutine takes two numbers and adds them together and returns a summation. Very simple, right? So here I need to pass two numbers, 2 and 7, right? So some subroutines, you need to pass some data. Some subroutines, they need to return some data, right? Here, for example, I need to pass 2 and 7, okay? And this one should return number 9, which is the summation, okay? It depends on the subroutine number. You should understand, guys, all the subroutines need to call and return. So these two are must be used all the time, right? However, these two can be optional. 3 and 4 are optional because some subroutines you don't need to send the data, okay, and you may not return the data, right? Some subroutines you may not need to send, but you need to return. Some subroutines you might not need to send and return, and so on. So it depends on the programming problem you want to do. So that's why these two are optional. It depends on what you want to do here. Okay, guys. So now this is to make any subroutine in any programming language. You have to find a mechanism or a way to go. You have to have a way to return. You have to have a way to pass data. You have to have a way to return from a subroutine, right? So now I'm going to explain them. How can we do these four things in assembly? So let's start with the first one. Number one, how can you call a subroutine? Okay, in order to call a subroutine, guys, we have two instructions. We don't have an instruction call. Call is not an instruction, guys. We have two instructions. In order to call a subroutine, the first instruction here is called BSR, branch subroutine, and then you put the name of the subroutine, right? Can be any name like keypad, for example. Okay. You can say JSR, jump subroutine, and then you put the name here. Okay, so you can use this one or this one. However, this one long and this one is short. So my opinion, for peace of mind, all the time you can use this one, and you may not need to use this one at all. You understand what I'm saying, guys? Because this is short and this is long, so you can use just jump subroutine all the time. Any question, guys? Okay. Now, this is the first part. How can you call a subroutine? So I told you, you can use B branch subroutine or jump subroutine, and then you put the name, which subroutine you want to go to, right? This should be written where you want to call a subroutine, right? So you know, as I'm going to explain later, in C language, and it's the same thing here in assembly, we have a main program and we have a bunch of subroutines. Same thing for C language, right? So in the main program, you can call a subroutine, right? Or subroutine can call another subroutine, right? We do that in C language, right? Same thing here in assembly as well. So now I'm going to explain. So for calling is easy. All what you have to do, guys, JSR, jump subroutine, and then write the name of the subroutine. Once you write this one, so you are going to, this instruction, you are going to go to the subroutine, right? Okay. Now, once, for example, I'm giving you example here, guys. I told you we have here main program, right? Same thing in assembly, we're going to have something like that. And then we have a bunch of subroutines. So this is a subroutine. For example, I'm going to call it keypad. So you can write the name here, and then you can put a colon this way. And then what happens here, how can you return from the subroutine, right? In order to return, we have instruction. In C, you don't need to use instruction, right? Once you have braces, the end of the braces means is going to return. Or do you have a return? No, sorry. Yeah, in C language, you also use the word return, right? Yeah, you need to return, I guess. So it's it's the same thing here. To return from the subroutine, we have an instruction. This instruction is called RTS, return subroutine, right? And yeah, so that means any subroutine, guys, any subroutine should start with a name, can be any name, colon, okay, and then you can put an instruction, and at the end you have to write RTS, right? This is a very good example, as you see here. This is the main program executing an instruction, and then an instruction, then instruction, then instruction, and then I came here. Once I come here, so I'm gonna go to the subroutine, then I'm gonna go. Once I hit return, okay, guys, I'm gonna go back to here, to next instruction after this one. Is that clear? Any questions? Okay. I want to tell you something interesting, guys, right? Again, this is hardware they don't understand, okay? One time, one student came to me and he told me, look, the program, everything is perfect, but it's not working, right? So when I checked the program, what I did, because sometimes when the program is, this is how it is always, guys, especially if your program is long, you may spend 1 hour or maybe 2 hours just looking for the error, okay? Once you find the error, you can quickly fix it. That's always my opinion. Usually fixing the error, it takes no time. Usually the difficulty is to find what's wrong with your code, right? Especially If it is not, if it is in the writing, the code error is going to give you error message, right? But if it is logical error, it's not going to give you error, right? Message. So I'm going to tell you what happened. So I looked at everything in the program. Everything looks okay to me, right? So I want to know which part of the program has a problem, right? So what I did, I put a breaking point here, and then I put breaking point here, one before and one after. And as I told you guys in the lab, using breaking points is very useful to find errors. Try again. If you have not used it yet, you need to tell the TA, or I already explained in the slides of chapter, in the slides of lab 1, how can we use the breaking point. So you have to think about it. So anyway, I'm going to tell you what I did. I put a breaking point here, and I put a breaking point here. So the program came to here, right? So that means everything here is fine, because the program came to before the subroutine, right? However, when I clicked run, right, the program never come to here, right? So I put here breaking point before and after. The program came here, but never come to here. What it means? It means my program goes to the subroutine but never come back, right? Because if it come back, the program would stop here, right? So the program didn't stop here. That means, so at least I was able to narrow it down, right? Instead of looking in the whole code, no, I'm gonna only focus what's wrong with your subroutine, man. I looked at the subroutine, I found very silly mistake. The student forgot to put RTS. You got what I'm saying? So if you forget to put RTS, what's gonna happen? I'm gonna tell you what's gonna happen. Look here, guys. As you know, your program here is gonna be stored in memory, right? As when it is converted to machine code, it's going to be stored in memory. So what happens if you forget RTS? So once you come to the subroutine, you're going to execute instruction, and then because you forgot RTS, it's going to take whatever in the memory. So it's going to go to, after this instruction, it's going to go to the locations in the memory. It's going to take whatever there, and whatever bytes are there, and then if these bytes by accident are instructions, it's going to execute them. If it is not a valid instruction, it's going to give you error. It's going to tell you, no, this is not a valid instruction. You got what I'm saying? So what's going to happen? Your program, after you finish, after the microprocessor executes all the instructions here, because you forgot RTS, it's going to go to the memory, right? Execute whatever there until it hits some ones and zeros that are not an instruction. It's going to give you error. Anyway, okay, guys, is that clear? Any questions? Okay. So again, all what you have to do, just use jump subroutine, and then you have to define subroutines this way. This is the name, colon, and at the end you have to put RTS. Don't forget RTS. And then once this instruction is gonna say, once you come here, we're gonna go to the subroutine here. We're gonna start executing instructions here until we hit RTS. Once it comes to RTS, so it's gonna return back. Okay, if it does not hit if it does not hit RTS, it's not gonna come back. RTS should return it back to here, right? Okay. Now, guys, this is how our program should look like, guys. From now, our program should look like that. Number one, I have here main program, right? And then I have a bunch of subroutines, as you see here. Okay. For every subroutine, you have to put a name, colon, and you have to put at the end RTS. Name, colon, RTS, this way. Okay. And then in the main program, you can go execute the subroutine and come back. Maybe inside the subroutine, you can call another subroutine and come back, and so on. Is that okay? So you can have a number of subroutines. That's okay. And also, listen to me. What's important, again, because this is machine hardware. So if this is the main program, we're going to execute an instruction this way, and all your program should be in memory, right? So all these programs should be in memory. Okay. So if I come here, guys, in the main program, execute, and then at the end, if you don't do something here, it's going to continue executing instruction, right? Because no one is going to stop stop. You have to do it by yourself, right? So that's why most of the time we are going to do one of two things, guys, right? In the main program, either when I come, I'm going to go back again if you want to keep repeating, right? So we will do this one all the time. Or, as I told you in the last lab, once I come here, I want to freeze. You have to freeze it here. Otherwise, if you don't do that, it's going to go execute the subroutines, right? So this is how we will handle the main program anyway. So again, your program now, guys, should have a main program, and also should have a bunch of subroutines, right? Every subroutine has a name, and at the end it should have RTS, right? And then the main program has to be one of these two guys. When you come here, you go to the beginning again to repeat, right? You will understand why I have to keep repeating. I'm not saying you have to, okay? It depends on what you want to do, right? So as you will see, for example, in next chapter, I want to get a number from the user, and then I want to do something, and this should be repeated, right? Anytime the user input some value, I have to take action. So that's why it has to be repeated, right? So it depends on the nature of the programming problem. Okay, here I don't want to repeat, but once I come here, I want to freeze it here. Otherwise, if you don't do that, if you don't freeze it here, it's gonna go in the memory, because always keep in mind this is a memory, right? So it's gonna go executing instruction in the executing whatever. It's gonna take whatever in the memory and consider it like instruction, right? So anyway, the last thing I want to explain now, guys, is I told you before I told you before we need a stack to execute subroutines. Without a stack, we cannot have subroutines, right? I'm gonna tell you why. Look, I'm gonna explain now. Look here, guys. I have an instruction, we call it jump subroutine. Once you come here, you have you have to come to here, right? And then once you come to RTS, you have to go back to here, right? I'm gonna explain how this is done by using the hardware. How the hardware will do that. Okay, so here you branch. Is that branch instruction? Yes, it is branch, but branch alone is not enough. I'm gonna tell you why, right? Because I have to keep this address somewhere. I have to store this address because I'm gonna use it later when I come to RTS. This address, we call it return address, right? So as I'm gonna explain right now, this one has to do two things. Okay, that's why branch instruction alone, you can say branch. No, branch alone is not enough, because this one has to do two things. Number one, it has to branch to here, right? Branch means in PC, it has to store the beginning address here in PC, right? This is how branch works, right? But before doing that, it has to store the return address. It has to keep it somewhere, right? Because I need it later. So I need to know when I return, where I have to return, what location. So this one actually, as you will see right now, is gonna do, this one is doing two things. Number one, it has to store next address, okay? Where in stack. So this one, again, you don't need to do that. I'm explaining how this instruction works, right? So what this instruction is gonna do, number one, is gonna store the next address in stack automatically, right? And then and number two is gonna store in PC the beginning address, so that next time PC come to here, right? So in addition to branch, so I can say this one is actually two things: branch and push. Branch and push, right? Or let me be more accurate: push first and then branch, right? So because this one has to push the return address in stack, and then this number one. Number two, it has to branch to here, right? So this number one. When I come to RTS is gonna take whatever in the stack, on the top of the stack, which should be the return address, put it in PC so that I return it back, right? So that's why I'm telling you, without a stack, we cannot do this story, right? Because this one has to store the return address in stack, so that this one is gonna get it from stack and return it back to here, because I have to store this value somewhere to know where I have to return. And this address, we call it the return address, right? And here, very good slide, very important slide, guys. I'm gonna explain it quickly, but next time for sure I'm gonna repeat it again. Very important slide. Now you will understand why what is the rationale, what is the logic behind last in first output? Look here, guys. When I call this subroutine, I'm gonna call F1, right? I'm assuming the address here is RA1, return address 1, right? So after I finish F1, I have to return here this address. So I have to keep this address in stack. So this one has to be in stack, right? Assuming when I go to F1, F1 is gonna call F2, right? So also this one has to be also stored in stack, right? So now the stack has RA1. When I return it from here to here, it also should have RA2 when I return it from here to here. Same thing when I move from, when I call this one, also the stack has should have RA3, right? And then when I call this one, it's gonna call this function. So the stack now has RA4, which here, right? It should be here, right? So now listen to me. So now I push this return, then this one, then this one, and this one, right? However, when I need them last in first output. When I need them last in first output. Why? Because I'm gonna return first from here to here. So I need the last one first, and then I'm gonna move from here to here. So I need the second one, and then and so on. That's why it is last in. Anyway, I think I already exceeded the time. So anyway, next time I'm gonna repeat it again, but very interesting. And that's why they created a storage space for to do last in first output. Because if you see here in this scenario, okay, I push this one, push this one, push this one. But when I return, I have to return first from here to here, and then from here to here, and then from here to here, and from here to here. That's why I need them in reverse order, right? That's why last in has to be first output. Okay. Anyway, see you next time, guys. Goodbye. So next time I'm gonna start chapter 3, right? So try to print the slides to take notes. Okay, bye.
I got a quick question.
Sure.
Is the homework due Wednesday or Thursday?
Sorry for that. It's always Thursday because you have to turn it into the TAs during the lab session. So always anything you turn in, it has to be during the lab sessions. Okay. I'm sorry. I know I made a mistake on the website. So I'm gonna correct it. Okay, thanks very much.
Oh, good. Thank you.